I'm excited to introduce our next speaker, Professor Sayat Ibrayev. He's the head of the Laboratory of Mechanics and Robots and Manipulators at the Institute of Mechanics and Engineering in Almaty. I hope I did not butcher that.
Yes, yes. This one. Thank you very much. My name is Sayat Ibrayev from Kazakhstan, Institute of Mechanics and Engineering, and maybe my presentation will not be of interest of the priority of this audience because I'm going to speak about very specific problem of robot design and mathematical aspects of this problem and theoretical aspects, and I will try to speak as brief as possible. But on the other hand, optimization of robots is one of the crucial aspects of robot design, and usually we deal with multi-criteria optimization problem, and our methods may represent interest to design any other kinds of robots, including such criteria as conflicting criteria, as kinematical criteria, the accuracy of motion generation, or dynamical criteria of force transmission or power consumption, and so on. And I am going to talk about our experience on designing of a walking robot. This is our institute, and leg propulsion has specific some advantages in comparison with wheeled and tracked robots or tracked vehicles. Here is excuse me. The second presentation I have with video. Alt is here, but I cannot. Oh, wait. We are there. Yeah. Not next slide, but no, next file. I have another file with video.
I think the video is not.
Not here, but in another file.
Okay.
Another presentation.
So we need to switch this.
And sure. So. Yeah, this one.
This one.
Okay.
Yeah.
Very sorry. Here. Excuse me, please. This is the prototype of experimental robot, walking robot. And first, before we have designed mathematical modeling of this robot. And before we have modeled propulsion mechanism, leg mechanism. But before this work, we have designed this leg mechanism in accordance with 4 criteria, including reproducing of generating of straight line trajectory and supplying transparent transference motion of the output link and force transmission, and also to meet the criteria of step circle parameter. And in order to make it more clear what is the object, I will show you first model of this robot and what we have designed in the beginning of the project. So this model works from only one motor, and due to the specific leg mechanism, it works and provides the possibility of adapting to surface irregularities. And sorry. This video files of a very huge size, and therefore was not possible to bring them together. Okay. So okay. So here we have the output link tracing following straight line trajectory, and also translatory motion, so that each point on this output link traces the same trajectory, and therefore it provides the possibility to adapt on uneven terrain. Here was example of model. This black mechanism is adaptation mechanism. Unfortunately, I don't want to switch to another presentation. And you know that leg propulsion has specific advantages in comparison with wheeled and tracked mobility, tracked propulsors, as high passability of unstructured terrain, no slip on loose soil, and less medium resistance, and less damage on supporting ground, which is very important for agricultural purposes. And adapting, if we provide adapting on terrain irregularities, then no additional power consumption is needed to for motion on over rough terrain, and the body of the robot can move in a straight line and translationally motion without tilting and despite uneven terrain. And these advantages were confirmed by experimental works testing over loose soil, sand, and swamp, and shallow water. And what is for agricultural vehicles? You know that existing robots have, existing vehicles, agricultural vehicles have high performance and work at high speed conditions, but they are very expensive and heavy and a very huge damage on soil. And trend points to swarm robotics, light and cheap autonomous robots supplied by AI. And unfortunately, when designers construct robots, walking robots, they most of them use biomorphic robots, but from mechanical point of view, many of them have irregular structure. For example, if we use a hexapod type robot with 6 legs, and each leg have 3 degrees of freedom, 3 actuators, and altogether we have 18 actuators, and a very huge problem of control will be have to be solved to coordinate these 18 actuators. Whereas when using the straight line mechanism as proposed here, only one actuator is necessary to provide straight line and smooth motion of the robot body, and the additional actuators can be used to turn, and individual adaptation system is provided for each leg, adaptation to uneven terrain, to terrain irregularities, and therefore it's not necessary to coordinate them. For example, if I have 6-legged robots, then at least 6 drives, 6 actuators are out of the necessity of coordination of their work, and this simplifies control. And on the other hand, for instance, here you see quadruped robot with 4 legs, and each leg has 3 degrees of freedom, 3 actuators, and altogether 20 actuators. And all of these actuators work in the mode of intensively accelerating and braking, which is so far away from saying that this is optimal from mechanical point of view, because huge energies consumption is necessary to actuate such robots. While in our case, we propose to use very simple mechanical device, mechanical leg, where the main actuator of crank link rotates with constant velocity, and providing constant velocity, we can provide of the crank, we can provide constant and smooth motion of the robot body. And on the other hand, if you calculate from point of view of theory of machines and mechanisms, number of degrees of freedom of such system, like hexapod, like robot, you will have, we will bring over constrained system, because the number of degrees of freedom are much less than the number of actuated joints, actuated motors. Therefore, we have statically undefined system, which is not possible from theoretical point of view. Of course, the modern means of control provide control with high accuracy, and it's okay, that's okay, but it can influence on additional resistant forces at motors and additional reaction forces in robot joints and slippage of food and other effects, especially when we want to increase the velocity of such system. The most promised scheme of the robot is used in adaptive suspension vehicle quarters of Professor Waldron from Ohio State University. Due to kinematical decomposition of the leg construction, so that one linear actuator is responsible for horizontal and smooth motion of robot body, and the second one on each leg is responsible for vertical motion of foot. But here we have the problem of reciprocating motion of these linear actuations that affects on the resource of the actuators of hydraulic cylinders. And so after 100 kilometers, you have to eliminate all actuators, all hydraulic cylinders. Maybe now the resources of the modern cylinders are much more better, but this is one of the problems. And on the other hand, if you have high speed, then these reciprocal motions require additional power supply, additional power consumption. And this is not effective from theoretical point of view, from mechanical point of view. And on the other hand, here prismatic joints, prismatic piers, sliders are used, having transverse loads in orthogonal direction. This also requires original solutions, constructive solutions, and expensive design. So we here proposed the mechanism which has only revolute joints, no prismatic joints here, and here the yellow link where we have actuator is responsible for horizontal motion of foot, and the green one is responsible for vertical motion of foot, and therefore this full decomposition of kinematical decomposition of motion will lead to optimal construction from energy supply point of view. And I will pass the following formulas and supplying the required horizontal rectilinear motion with high accuracy is provided by synthesizing, by determining the link dimensions, sizes of links with the help of least square approximation problem, this specific mathematical problem. And the meaningful result here is theoretical results that we obtained analytical solution for a very huge number of parameters, but here for this audience is maybe not so very interesting. And functional study of the studied mechanism was provided, and here we can see that the scatter of parameters in the left side we have red, the spread of parameters, the best parameter values with best accuracy. And in the right side, we have this the most better good parameters values from point of view of force transference. And we see that this we have here conflicting criteria, this accuracy and force transmission as usually such problems arise always in mechanical constructions, and the problem is to find compromise solution. And we have not 2, but 4 such designing criteria, and we deal with multi-criteria optimization problem. Here is the final optimal compromise solution is shown here. This slide demonstrates this black mechanism is adaptation mechanism of each leg, which provide adaptation to uneven terrain, so that this mechanism provides smooth horizontal and translational motion of the body, despite despite terrain, rough terrain irregularities. Here, as I said above, there was this is well-known construction of adaptive suspension vehicle using pantograph mechanism with decoupled motions, but as I have said, it uses linear actuators, and disadvantages that I have said before. And here, to optimize this structure, we have used the theory of optimal designing of so-called parallel robots. Usually, you know, anthropomorphic robots have open loop construction, but if you want to increase the rigidity, the stiffness of the system, it's more preferable to use parallel type robots, so-called closed loop kinematical chains, and these such structures are used successfully in machining robots, for machining of details in machinery and other fields. And this theory was applied for walking vehicles. And the isotropy condition is the most important result of this theory, and we applied these results here to obtain such optimal design of walking robot leg. And here I will pass all theoretical moments, and this solution was obtained by analytical solutions was obtained for least square approximation problem. And if you use Chebyshev norms, then you deal with minimax problem, and the solution was obtained as linear programming problem solution. And various methods were applied, and the comparison of them is presented here. I will pass all these results, and isotropy condition was applied to optimize walking robot construction. Due to adaptability of each leg on terrain irregularities, it's possible to consider kinematically equivalent planar scheme of the robot when you view from above. And for this planar scheme, the optimal parameters from point of view of optimal force transference was considered. Here is geometrical interpretation and very huge formula that I will pass, and these ones may be more understandable. And after some transformations, which made by Arman Ibrayev, which is post-PhD doctorate of this KAUST University, being the student, and here she obtained geometrical interpretation of these results. She have obtained 4 results. And then we completed the theoretical study of this robot, and now we are going to manufacture final experimental prototype. And if everything will go okay, then we will develop this project further, considering navigation and mapping, creating SLAM software adjusted for robot. Thank you very much.